So what we'll do today is we will be starting with the concept of routing and switching, right? More importantly, switching will cover today, right? So we've been telling from the beginning of the session that we are routing the packets through layer 2 or layer 3 using routers or switches, right? So why the concept of routing and switching is actually important. Basically, each layer, if you see in our OSI model, that is in the layer 7, we have application, layer 6, we have the sessions layer, and we have the fifth layer, which is, what's the fifth layer, guys? Hello? What is the fifth layer according to OSI model?
Session layer.
Okay. What is the sixth layer then?
Presentation layer.
Right. Sessions layer, transport layer. Okay, and the application layer. Now, whatever traffic, whatever application traffic we generate, right? Whatever we are doing right now, I am trying to, draft here something, I'm typing something, and you guys are listening to what I'm telling. So all the data is going from the application layer towards the physical layer, right? And whatever is here until layer 4 is something which is in the software, which is internal to my internal network interface card and the processing, and internal to your network interface card and the processing, right? But something which happens on the physical sphere, so which is in the hardware layer, is nothing but our network data link and the physical layer, which is the cables and the ethernet, right? So when we come to the network layer, its basic job is to route the packets using the IP address, that is using the logical addressing, right? So we use IP address in order to route the packets from one point to another point, right? And this happens using what? Using routing protocols. Okay. Now, what about layer 2? Layer 2 is nothing but we route the packets using the physical address, right? You route the packets using the physical address by identifying or by understanding or getting to know about the MAC address or the IP address of the next hop. Let's assume that this particular router is there and this particular router is there. So using ARP packet, you will be knowing the MAC address of this particular destination, right? So that we have learned in ARP. But then how will you send the traffic within the physical layer? So that we use using switching protocols, among which the only protocol what we have is VLAN, virtual LAN. And today we are going to discuss about this, right? We'll discuss about VLANs, we'll discuss about STP, we'll discuss about RSTP, right? Very important. Okay. Now, what is a VLAN? VLAN is nothing but,
Virtual long area network.
right. So, what does it do? What's the basic thing it's going to do?
It's connection of devices virtually rather than physical kind of thing.
No, let me clarify.
Yes.
Basically, basically what happens is, if, for example, we have an organization, in an organization, do we have only one department? We have multiple departments, right? So let's divide those into different departments. So now each floor has one department. Let's say this is HR department. This is sales department. This is development department, right? This is the QA department, right? Now, the basic core job of VLAN is only keeping the data within the respective departments, right? Just keep the data here. Just keep the data here, here, here. We do not want the data to get out and go and talk to whatever HR is trying to broadcast. We don't want that data to go to the sales team. Similarly, the sales team data should not go to the development team, and also it should not go to the HR team. So to avoid that, what we do is we divide the network into segmented networks. That is nothing but the virtual LANs, right? And the basic definition of this is to divide the broadcast domain into smaller broadcast domains, right? To avoid broadcast storms or collisions, right? Now, what do we mean by broadcast storm? This is what you are going to use if you try to answer in an interview, right? So you are going to use this terminology, broadcast storm or broadcast collision or packet collisions, right? So now, what do I mean by that? Let's say the HR team generated a broadcast packet, and let's assume that there was no virtual network here. Right? So let's assume that there was no virtual network which was configured. Now, when you broadcast something from the HR team, so they will be sending the packets which is destined to the broadcasting destination IP or destination MAC address, right? Just give me a second, guys.
Yes.
Yeah, yeah.
Team, I'm sorry. I had some urgent business to look after. So, right. So we were discussing about VLANs, right? So VLAN and broadcast storms and collisions we were talking about. So what if the HR department is sending a layer 2 packet? It's trying to broadcast a message. Let's say it is sending some broadcast message, and I believe I have told you earlier that MAC address for broadcast is FFFF F. So it will be like this, right? Right. So now, when the HR department is doing this, what will happen in this network? In this whole infra, what will happen? The same packet will go here, it will go here, and it will go here also, right? So you see how much unnecessary data we are sending through the network. They do not need this. They do not need HR's broadcast message, but still we are sending it. These guys don't need it, but still we are sending it. These guys also don't need it, but still sending it. So it is an unnecessary utilization of resources and also a security risk. What if the HR team was discussing about salary packages internally among themselves, and they wanted to inform to each and every person in the HR department that for a QA the package should be so and so. For a developer, the package should be so and so. For the sales team, the package should be so and so, right? And unfortunately, because of this particular this particular architecture, it reached to them. So that's a security risk also, right? On that note, something called as VLAN was introduced by Cisco, right? Now, what and how do we configure VLANs, right? So VLAN is nothing but an ID. So it is just an ID which is of 12-bit size, right? So it is 12-bit size. So 2 to the power of 12 is nothing but 4096 VLANs you can support in one switch, right? So 4096 VLANs can be configured on one switch, right? Now, what is the main role of this particular VLAN ID? Now, when you are trying to send, so let us take the same example here, wherein the HR department was sending the packets in, it was broadcasting the packets internally, right? So, what and how it will happen? So, let's assume that we configured the network in such a way that HR department's VLAN is having ID as 1, the sales department's VLAN ID as 2, and the development team's VLAN ID as 3, the QA VLAN ID as 4, right? So when this happens, the router or the switch, whatever we have configured, so whatever switch or the router we have configured with the VLAN configuration, that is going to check what's the VLAN ID when we are sending the packets. If the VLAN ID is within that particular VLAN domain, the VLAN ID within that domain, that packet will only be forwarded within that VLAN, right? So if any packet is sent within the VLAN ID 2, so within that domain, it will be forwarded within this domain only. So it will stay intact here. It will never go out, right? So based on that, this is how the definition of VLAN comes into picture. So division of a bigger broadcast domain into smaller broadcast domains. So what we have done here, we have divided the overall organization's broadcast domains into smaller broadcasting domains, right? So we have divided it. We have divided into 4 broadcast domains using VLAN IDs. Okay. Now I have some images as well. Right. So now if you are looking at this image here, if you see here, this particular switch is connected to this device here, the 12, 11, 12, 21 and 22, 23, 24 here, and 13 and 14. Now if you see here, what is happening? We have VLAN 20. We have 21, 22, 23, 24. These PCs are in VLAN 20, right? And 11, 12 and 13 and 14 devices are in VLAN 10. So the communication will remain within themselves, right? Now let's take an example as I have shown you here. Let me take a newer example. Let's say that this building is of 4 floors, right? The top floor is occupied by the HR department. The this floor is occupied by the developers. The next floor is occupied by the QA, right? And the ground floor is again occupied by the HR team, right? Now, how will they communicate in between each other? So definitely there is a switch here, there is a switch here, there is a switch here, there is a switch here. Now we have configured the VLANs. So this is 1, 2, 3 and 4. That is what we have configured, right? Sorry, not 4, this is 1, because this is also the HR department, right? 1, 2, 3 and 1, right? Now the communication should happen in between this HR team and this HR team only, because the VLAN IDs are 1, right? And we are connecting the switch also like this, right? So we are connecting the switch, right? So we are connecting the switch like this. Is it a good way of connecting the switches? So definitely it is going to work. Definitely it is going to work. It is going to send the packet which are relevant for the VLAN ID 1, that is for the HR team. It will reach the HR team only. It will not go to developers. It will not go to QA. But are you seeing how much clutter we are creating here? We have switches per floor. That is okay because those are the physical devices. But if you see the cabling, we are unnecessarily utilizing the each port, which could actually be used for connecting to some other useful devices within this floor, right? So if you are aware of a switch, I believe we had a portion where we saw the switch image and all. No worries, I'll fetch it from Google. So the switch is generally a 4 port switch, a 8 port switch, right? A 16 port switch, a 32 port switch. So like that, there are different configurations and different ports are there for a switch. So Cisco provides those sort of switches. Not only Cisco, Juniper also does that, right? So Juniper is another organization, Cisco is another organization. It has its own OS, Cisco has its own OS. Now what we are learning is all relevant to Cisco because all the protocols, ports and everything have been developed by this particular organization here, right? But when in future, if you are going to work for a Juniper OS, in an organization, it is nothing different from Cisco. The only thing what changes is the configuration part, right? So the configuration part will change. The commands will change when you configure a router, when you configure a switch, right? So now, why I am telling you this particular scenario is wherein we are avoiding this clutter is because I would like to introduce you to the concept of trunking, right? So there is something called as VLAN trunking port, VTP, right? What's the major use of this? So when you use virtual trunking protocol or VLAN trunking protocol, what it is going to do is it is going to help you send the Ethernet frames or the layer 2 frames along with the tagged VLAN ID with it through the network on a single cable, right? The reason being we are adding an extra header here, which is the 802.1q header, which is having the VLAN ID mentioned in it, right? And that is how in this second image we see how it actually looks like. If you see here, the earlier switches were connected with separate links altogether in order to communicate within the VLAN. It was a good architecture, that's fine. But what if we have a bigger organization, very big organization? You cannot go ahead and unnecessarily utilize the ports here, because they can be used for another device, or they can be connected to a telephone link line, something like that, right? So now in order to avoid that, there is a concept called as internet switch link, or 802.1q. So dot q is what we call it, right? This particular thing is what we are currently using. Internet switch link was something which was earlier, before the advent of IEEE standard 802.1q, right? So Cisco used to use this earlier in its header, Internet Switch Link, ISL. It used to add that here within this particular data link layer. In the data link layer, we have the MAC addresses, what we see there, right? So that particular header, or that particular header what we have, that had earlier, it had internet switch link, which is not at all relevant now, and no need to learn about that also. The major thing what you have to learn is about IEEE standard, that is 802.1q, right? So that is what is shown here. What does it do? So it consists of the type, the priority, flag, and the VLAN ID, right? VLAN ID is what we are currently discussing. So this is what it will carry when it is sending the data. When this switch is trying to share some data with another switch, right? Whenever they are trying to learn about the MAC addresses, whenever they are trying to update their own MAC tables internally, when it is connected to the trunk port, I'll come back to what does a trunk port mean. So when it is connected to a trunk port and trunking is enabled on that particular port, what is going to happen is the data from this particular switch to this particular switch will flow, right? But it will flow along with the VLAN IDs of each device. So this particular device MAC address will be tagged with the VLAN ID 20. This particular device MAC address will be tagged with the VLAN ID 20. Now this switch will be aware of this particular configuration, and this switch will be aware of these two device configuration. So whenever a packet is coming from switch 2 to switch 1, let's say this guy wants to communicate, this one machine wants to communicate with 2 here in this particular floor or this particular section, right? So whenever the packet will reach to this switch, the switch will immediately identify, okay, this guy is belonging to VLAN 20. Let's send him to the VLAN 20 here on switch 1, where it is residing in this particular portion, because it has the MAC address and it has the switch, the VLAN ID, right? So that is how this VLAN trunking protocol is useful, right? Also, VLAN trunking protocol is useful in another concept that is called as inter VLAN routing. Team, which whatever I am trying to tell here, right? This is not something which I am telling extra. It is something which is really important and can be asked, and not can be asked. This is something which you must be aware of. So whatever I am telling here, take screenshots, try to make notes. If you are not understanding anything, if you see IEEE 802, just make a note of it in your notes. Later on, you can ask me or you can search Google. That's not a problem. But whatever I'm trying to impart here, whatever I'm trying to tell you here, this is something which is required, right? So with VTP, virtual trunking protocol, there comes another concept which is inter-VLAN routing. Right. So let us see here. Now, this particular machines, these machines are in VLAN 10, right? And these machines are in VLAN 20, and they are connected to switch. So this switch is shown like this in a broken format. The reason being they cannot communicate with each other. Why? So this switch here, the switch here which is connected for VLAN 20 and the switch here for VLAN 10, they are completely separate domains altogether. For the switch, for the switches, these are separate domains. I told you just now this something called as broadcast domain, right? So here we are creating two broadcast domains, VLAN 10 and VLAN 20. They are not at all relevant to each other, but still I want them to communicate. The reason being, I want the VLAN 20 people's MAC address to be known to the VLAN 20 switch, right? So how will you do that? You will be using L3 switch. So there are some networking devices, that is I told you earlier, router which acts in the layer 3, right? So router which acts in the layer 3 and layer 2 which act where we see the switch, right? But when something is required for us, like you want to communicate within from one network to another network, for the purpose of layer 2 we use something called as layer 3 switches. Layer 3 switch. So basically layer 3 switch and router, the major difference between that is the router has additional routing capabilities. It has more and advanced things which are relevant to routing specific protocols, right? But in layer 3 switch, the main purpose of layer 3 switch is to route this inter VLAN routing. In order to create that particular atmosphere, we use this L3 switch, right? What it is going to do, it is going to have the routing protocols which are going to tell that from this particular subnet there is a routing protocol which is configured for to reach this particular subnet using this router here, because this router is connected on this interface F00 and this router is also connected to this interface F01, right? So there is a routing protocol which is going on here. So this router sees that there is a subnet 10, there is a subnet 20. I have to route those packets from this subnet to this subnet via the protocol, whatever the admin has configured, right? So now what will happen is whatever layer 2 packets are there, that is going through this router towards this particular section using the L3 switch, what we see here, right? Now that is what is happening with the L3 switch. So what we are trying to do over here is we are just trying to send the layer 2 packets through the using the layer 3 using L3 switch, right? Any queries so far? What is the concept of VLAN? What is VLAN trunking protocol, right? And the VLAN ID, which is having around 4096, right? So another concept is nothing but the normal range and the extended range. So when you purchase a Cisco switch, so if an organization purchases a Cisco switch, the moment it comes out of the box, it is plug and play. There is no need to configure. There is nothing the admin has to do literally. Once it comes into an organization, they just bring it out of the box, they put it into the stack and they connect it to the cable. That's it. So the whatever ports are there, they will connect it to the port here. That's it. And automatically the switch learns everything which is happening within the network. The reason being, it has this normal range enabled within that 1 to 1005. But what if your organization does not want to follow the standardized practice? They want something custom for their own organization, or there is some other requirement. In that portion, what happens is you configure the switch. So you connect your device, right, to the switch, and you open the command line interface of the switch, and then you start typing the commands. That is config t. I mean config t is nothing but config terminal, and then from there you configure the switch port. Then you give the switch port access VLAN ID. So all the configuration commands you will be giving when you configure a switch. Accordingly, you will configure it for your VLAN and whatever purpose you have to meet there, right? So This extended range and normal range is nothing but the moment it comes out of the box, it is going to be capped at this particular normal range. That is 1 to 1005 VLANs only you can use. But if you want to use more than that, let's say your organization is big, it's large, and you require different VLANs in the same network. In the same network, you need require different VLANs. What you are going to do? You're going to use this extended range where you have the capacity of reaching until 4096 VLANs. So that's way too much for an organization. And that is going to provide security, right, and privacy. So what is the main purpose of VLAN? It is just to divide those broadcast domain. So for example, what you can do in your home also, on your own router also, you can create VLANs. It's a simple job, right? What you have to do is you have to give it a VLAN ID. Let's say you give it VLAN 1 and then assign this VLAN to the guest Wi-Fi network at your home, right? So now what will happen is whatever traffic of this guest Wi-Fi, let's say you give your guest, whoever is coming at your home, you give them the guest Wi-Fi password. So very easy password you'll be creating like some ABCD, EFGH, something like that. And then you give to the guest. The guest will log into your network, but they will be connected to the VLAN 1. So they will not be able to check your traffic. Let's say the guest who is in your home is good and well versed with hacking and all, right? The moment he connects to your network, he can hack if you do not have a VLAN specified there, right? But if you have a VLAN specified there, the conversation, whatever he's trying to browse, whatever he's trying to send, or whatever he's trying to do, remains within that domain only. That is within the VLAN one. Whichever VLAN you are configuring yourself in your particular SSID, it remains within that particular VLAN only, right? Now, why is it that we are capping 4096 only? Why only 4096 are there? The reason being VLAN ID has a size of 12 bits. What is 12, 2 to the power of 12? 4096. So that many number of VLAN IDs is what you can create, right? So I believe everybody understood what is an L3 switch. It's a device which is acting in between layer 2 and layer 3 for the purpose of for the purpose of establishing communication between the VLANs, which are in different subnets. That is important. Now this subnet is not related to layer 2. This is related to what? Layer 3, right? So we have learned previously what is subnet. In subnet we have learned for class C /24, for class B /16, for class A it's /8, right? So these are different subnets. But what if I want communication between these different subnets and I want the VLAN IDs to be known to them? What you're going to do? You're going to configure an L3 switch in order and provide routing in between this particular section and this particular section, and then you will route the packets, and that is how the switch will understand that there is a device having so and so VLAN and so MAC address. All right. Now I told you about VLAN trunking protocol, but I am telling you about trunk. So what is trunk? What is access? So trunk port and access port. Now there is nothing to confuse here, right? So it's the simple thing that when you get a switch, right? So there are ports on it, right? So these ports, they are free. So they are once you attach a cable here, it's going to start forwarding the packets or receiving the packets according to the configuration. So switch has ports here and it has the ports on its other side as well, right? In order to send the packets and receive the packets. Now, what if you want to send the you want to configure a virtual trunking protocol here? You want to configure the VTP here on this particular port. In order for this switch to share and receive the shared information for all the VLAN IDs. Then what you will do is you will be configuring a trunk port. So this particular port will be designated as trunk port. What's the job of trunk port? The main job and role of trunk port is it can receive and process. It can receive and process the VLAN IDs, multiple VLAN IDs, right? So if I give you an example, let's take this as an example. Where is this? Yeah, this one. So now here we see that this particular switch is trying to share, this particular switch is trying to share all the VLAN ID information what it has got with this particular switch, right? Or vice versa, or this switch could be sharing the information. Now you see the same cable has two VLAN IDs mentioned here, 20 and 10, right? This is only possible when there is a trunk protocol to which this cable is connected with. That is only when you will be having this particular tag which will be mentioned inside the header, inside the data link layer, right? So in order to share and in order to receive that particular or process that particular information, you need a trunk port. That is the only port which is going to view and see which particular VLAN ID the traffic is going to. But access port is not like that. Access port is, it's not going to be concerned about VLAN ID. Hello?
Hello.
Okay, I had some network issue, I believe. Where did we stop? Was it access port or was it trunk port?
Trunk port completed.
Okay. Okay, so basically, we were discussing about trunk port and the access port on a switch, right? So what does this access port do? So it's not going to be considered about the VLAN ID. It is it is only going to accept which is untagged, which doesn't have any VLAN ID to the frame, right? So what it is going to do? Let's assume that there is an access port here which is configured here and here, right? And here also the access port and here also the access port. It's not going to send the traffic, send the packets from this switch to this switch for sharing this VLAN. So the network will not be able to communicate because these are access port, right? It does not accept connection for VLAN tags. But if this particular access port didn't have any VLAN configuration, right, and only it was connected via a cable or a link, then it would have sent, or this particular device could have communicated with this particular device, right? That's the only difference between a trunk port and an access port, and that is what is required. That's it. Okay, now we've been discussing about how the VLAN works, how it is basically configured. Configuration part, I'll try to show you in a short while how it actually looks like in a command line interface. But once you understand VLAN, the VTP, the trunking protocol, inter VLAN routing, these are something a little bit important, right? In an interview, you can be asked a question that VLAN specifications you will be answering, but they will ask you a simple question, that is, how will you communicate between different subnet VLANs? The answer is right here, that is inter VLAN routing, right? These particular things what I'm telling here are just single lines, or whatever terminologies I'm telling you, but these are relevant to the configuration perspective on a switch, on a L3 switch, on a router, right? So that is how it actually works. I'll show you the configurations shortly, maybe in the next session or something like that. Right now, we have learnt about VLAN, the configuration of VLAN, how the actual header looks like, what is the additional header which it adds, that is 802.1q, right? That's the IEEE standard which is given for the VLAN header. Okay. Then we have discussed about VLAN, inter VLAN routing. What is an L3 switch? Now, I believe we have discussed earlier about time to live packet in layer 3, and this we use to avoid loops, right? To avoid loops of packets, looping of packets. But how about in data link layer? What single mechanism we have, or what mechanisms do we have in order to avoid loops of the packets? So let me show you this example here. I think we don't have that image. Right, let me just take this. Just don't see what we are seeing here. So let's assume these three switches are connected to each other on their own interfaces. Now, when you see a diagram like this is how you will be maybe asked the questions also, asked in the interviews also. So this is a switch, and this number what we see here, these are the interface names, what it has, right? So G is nothing but the gigabyte interface of this particular switch, and the interface number is 0/2. This is 0/1, this is 0/2, 0/1 of this switch, like that, right? Now, what I'm trying to tell you is how the loop happens within the network. So let's assume this is a network, right? And here one device is connected, here one device is connected, here also one device is connected, right? Now this guy here simply he sent, or maybe he is new in the network, his device sent a broadcast message. What is broadcast? Broadcast is nothing but FFFFF, right? So it has to go to everybody. How will it happen now? Let me show you. Now, first I will show you in a simple way. So first the packet will go to from switch 3 to switch 1, then it will go to switch 2, then it will go to switch 3 again, and since it's a broadcast message, it will again go to switch 1, it will again go to switch 2, it will again go to switch 3, so on and so forth. It will keep rotating. Now this is the one side flow which I have shown, right? But once a packet of broadcast or a packet comes on an interface, it came on switch here, so it is going to egress out of this, and it is also going to egress out of this, right? Now what I mean by egress? Egress is nothing but going out, right? What is ingress? Ingress is incoming traffic. That's it. Right. So now this interface is going to broadcast the packets. Now since this image is really small, I will not be able to quickly show. We just cover this up. So just remember that there was a flow this way, right? The flow was this way because the broadcast packet is this side. Now the packet also went this side, and it went this side also. It went this side also. So the flow is this side also. So you see how network congestion you are creating. These all links will be congested, and the performance will be poor, right? So let's say that we are watching some YouTube video, right? And there is an interface here which is connected to internet, right? Now because of this loop, because of the packet loop coming up here, what is going to happen is it is going to congest the network here completely. This particular switch is completely processing things. It's going to overload the CPU of this particular switch, right? So and that is of course formation. In order to avoid that, there is a concept called as spanning tree protocol and rapid spanning tree protocol. Both are same. The only difference is if I take forward, let me understand this. I'll not tell you now. I'll tell you later. Right? So what is spanning tree protocol? In spanning tree protocols, what happens is let's this image only. This is better. Right. So in spanning tree protocol, what happens is we create the switch. Let's assume. I'll just tell you in a button knowledge. What happens is we create one port as blocking port, right? So I created a blocking port here. Right? This switch has a blocked port here, and all these switch ports are forwarding ports. Now let's say this device from here sends a broadcast message. Now that broadcast message will not egress out of this particular interface. It will go here, it will go here, and it will be logged here. Logged in the sense it will be logged here. So once the packet is logged, it is not going to come back. So there is no looping, right? And that is how layer 2 packet loops are avoided using spanning tree protocol or RSTP protocol. You can tell this in an interview. The simplest way of explaining how spanning tree protocol actually prevents the packet loop in the layer 2. Right? Now, how does spanning tree protocol work? Right? And that image is what it is here. Now, in spanning tree protocol, what happens is there is something called as an election process. Root, switch, election. And then this happens automatically. Right? How does this happen? Now what happens is each switch has its own PID. Right? If you see here, the bridge ID, right? And it has its own MAC address. So if you see here, all the switches here are having this particular switch has its PID as 3276, 3276, 3276, 3276, and everybody has the same PID. But the MAC addresses are changing. Of each device, the MAC address is different. Now in the election, what happens is, let's say this is one switch, this is another switch, this is another switch, and these three are connected. Now these three have to decide who is the root switch. what is going to happen? These all the switches, because they are in network, for every 2 seconds, every 2 seconds, this happens in the network. So this is standard. What happens every 2 seconds is each and every switch will send a BPEU hello packet, right? Which consists of the bridge ID and the MAC address of the sender. Right. So here this particular switch is going switch 1, switch 2 and switch 3. Right. So this switch is going to send a hello packet out of this interface and out of this interface. Switch 3 is also going to send the same thing. The switch 2 is also going to send the same thing. But they are going to advertise their own EID and then their own MAC address. Now, the next step is for each and every switches, once they receive the packets from the adjacent switches, let's assume in the case of switch 1, it receives the packets from switch 3 and switch 2. It sees that the PIDs are same. Let's say the PID was 1 here, 1 here, 1 here, but the MAC address will be different. Right? So when the PIDs are same, the switches get confused. Who is the root switch? So that is a big confusion. In order to avoid that, what the team has done is they have taken the help of MAC address. Now you tell me, how is MAC address helpful?
MAC address will be different for different.
Exactly. Because it is unique. Because it is unique. And if your MAC address is unique, it has a value that it will be less than the adjacent switches, or it will be greater than the adjacent switches. And always remember, in networking, the least value is what is preferred. The least value is always preferred. This is going to be helpful in the next concept also, and also in the routing. Right? So what will happen if the PIDs are same? If the bridge identification IDs for the switches are same, it is going to, the other switches are going to see the MAC address and they are going to compare with their own MAC address. Let's say this guy's MAC address was 2. I'm not writing it in hexadecimal format, I'm just taking it as a notation. So this guy's MAC address is 2, this guy's MAC address is 3, this guy's MAC address is 4. Right? Now this switch sees that mine is the least MAC address. Right? I'll become the root. I'll become the root. This guy tells that I'll become the root. The reason being, he says that the MAC address is lesser than these guys. Now this switch and this switch will obviously, they might have received the hello packet. Yes. And since they have received the hello packet, they already have compared their own MAC address with the MAC address provided by switch 1. So now this guy sees that, okay, 3 is greater than 2. I cannot become the root. So it drops from the election. What it does, it tells that, okay, let's assume that switch 1 is the root. That's it. And switch 3 also does the same. It also drops out of the election. Right? It is, you know how it is. It's like a leading party won by majority, and whoever lost, or whoever in the opposition, or the other parties which were not in the opposition, they joined with the leading party. The opposition also came along with the leading party. So the leading party becomes the root here. The other switches become the non-root switches here. Right? So everybody understands the election process in an STP. Right. Now the other concept. Now this switch is the root. Right? On that note, for this switch, this particular port, to whichever Ethernet cable it is connected, this particular port becomes the root port. Root port. And for this switch, this particular port becomes the root port. Done. That's it. So for the switches, the non-root switches, whichever port is connected to the root switch, that is the root port. right? Now the other port which is remaining is nothing but the designated port. The designated port. Now what is designated port? The designated port is nothing but it is the port which is going to the forwarding packets or receiving packets. That's it. Right. So what is the job of root port? Root port is nothing but in order for the switch to understand which is the least count, least hop count for it to reach the root switch. That is the root port. So for this particular switch, the root port will be this because this is the least hop count for it. If you see this in a diagrammatical fashion, this looks very easy to understand. But when you go in a larger organization and you have a larger blueprint of the topology, of the network topology, what happens is there we start calculating the root cost, right? So for each switch, if you see this diagram, this is the root switch here, as we have also taken in the diagram down below, and we see that for this particular switch, the root cost to reach here is zero because for the switch one, the root cost is zero. The reason being is this is the root switch. It does not need to go to switch 2 or switch 3 for establishing or sending packets to the root because it is a root itself. That is the reason why the root cost is equal to zero here, right? But for this switch and this switch, the root cost will vary. How will it vary? If you see this interface, it is advertising itself as 5. Right. That's the interface root cost. That is how it is calculating automatically. It is not like it is one hop and it should be one. No. So based on the interface root cost that is predefined on the switch, it is going to add up the numbers. So since the root cost is 0 here and the interface cost is 5 here, 0 plus 5 is equals to 5 in this scenario. So for switch 3 to reach the root, it will have in its map. So it will map that. It will create a table that destination MAC address, right, and the interface name and the least cost or the root cost. It will create a table within this switch like this. Similarly, for this switch also it will create a table like this. And how will it calculate? It sees that this interface is 4, right, and this interface is 4, right. So 4 plus 4 is equals to 8. So to reach from here to here, it has a root cost of 8. So that is how it's going to calculate that. Right? No, it is not 4 plus 4, 8. It is going to be 8 for this and it is going to be 4 for this. Because the interface, it is telling us that this particular interface is 4. The root cost it has, which is configured. Right? So it is not like one hop is equals to 1. No. It is the interface and it depends on that. The root cost depends on that. Right? What's the significance of root cost? The least the root cost, the more preferable the route for the device, right? So in this scenario, for this switch to reach the root, if you calculate the cost, it is 4 from this side. It is 4 from this side. But if it has to go through this path, it is going to be 4 plus 5, which is equals to 9. That is greater than this. So that is how the switches will decide whether it should go through this interface or whether it should go through this interface. Because we are humans and we know that this is going to be longer and this is going to be shorter, we can interpret this information. But for switches, numbers is what it looks after, and that is the reason why root cost was introduced, right? So once the root cost is decided, it is going to see the least root cost and then it will route the packets accordingly, right? So this is how STP and the STP election process works. Okay, now anything I'm missing? This is fine, right? So now what happens is, let's assume this switch were connected, but suddenly the connection broke here, right? So the connection broke. This is called as STP convergence, right? STP convergence. What does it do? Now, once it breaks, do you see what is going to happen? This guy who was the root earlier will not be a root now. The reason being, I told you just now that every 2 seconds the messages are sent, right? Every 2 seconds the BPDU hello packets are sent. But now there is no hello packet received by this guy and this guy. So now they understand, okay, something is wrong with the network. Something is not wrong with the network. I think we should start changing our topology and we should start changing the MAC table what we have, right? How much time does it take for that? Because you see an organization very big, let's assume there is some Google organization and everybody is working on highly they are working on highly escalated projects which require immediate finish, or immediately there is a deadline to that and all. And at that specific time interval somebody pulled the cable out, or maybe it got broken or something happened. So you see the amount of disruption it is going to cause within the network just because of one cable which is lost. So what happens is, the moment this particular thing happens, STP kicks in with the timers, right? So what it does, those 2 seconds hellos is what these switches will be waiting for. And for now, this guy will be sending a hello, this guy will be sending a hello, right? And this guy will be sending a hello, but this cable is broken. So the hellos will receive here, right? And the hellos will receive here from here. That's it. But there is no connectivity here and here. Then what will happen is the difference will change. After that, what will happen? It will wait for 15 seconds. So these all ports, this port, which were earlier, I told you, right? One will become as a root port, and the other one will become a blocking port in order to avoid those loops, right? So what is going to happen is this particular blocking port will go into listening mode now. The reason being, if it would still stay in blocking mode and this connection disrupts, this packet, whatever is trying to send the information from this switch to this switch and this switch, that packet is not going to be received here. So again, the STP a root election process will be disrupted. In order to avoid that, the interfaces wait for 15 seconds, and after 15 seconds it's going to start listening in the sense, whatever data you're receiving, I'll just try to listen and process it. That's it. Then what it is going to do for 15 seconds, after this 15 seconds timer, it is going to start learning. That is, what is the MAC address of this, what is this, what are the broadcast packets it has sent, right? What type of packet is it sending? It is sending a hello packet, or is it selling that I am the root packet? Is it sending a superior hello packet or a worse hello packet? So I told you that in the election we send the hello packets, right? But what if this guy becomes root? So what kind of packet it will send? It will send a superior hello packet, right? Once that hello packet goes, the other people understand that, okay, somebody announced that I am the root. That's it. Okay. Now, when these states change in the STP timers, 15 seconds of listening and 15 seconds of learning, later that port becomes forwarding, because within this 15 to 15 seconds, within this overall 30 seconds, it could not confirm who is the root switch, right? For that purpose, it start forwarding in order for the port to send the packets, whatever the switch is trying to send, and whatever packets it is receiving, it will process and then again send it back, right? And accordingly, because this link is broken, it is again going to do a root election process. And once that election process ends, this guy will again become the root, because of the BID and the MAC address is less, but the root cost numbering will change now, right? Because this link is broken, the switch 3 MAC table will remove the link mapping for this switch 1 from here. So switch 3 to switch 1, there is no direct connection. So it is going to make a note of it that for reaching switch 1, I have to go through this particular root cost, which is 8 plus 4. right? So that is how it is going to do. That is how it is going to again create the entry within its MAC table. So that much process goes in if there is a link which breaks suddenly, right? Now, what's the major difference between STP and RSTP? The only difference in is the changing of state and additional alternate port to avoid convergence. That's it. So what does this alternate port mean, and what is this the changes we are seeing here? So if you see here, I told you that the port is a designated port and a root port is there. But in RSTP, what happens? The moment this RSTP configuration works here, not STP, but RSTP, when it works, let me just clear this. So what it is going to do, it is going to create for the other switches an alternate, just an auxiliary port, right? It's just an extra port what it will create, and it will make a note of within the switches because RSTP is configured. What happens because of this alternate port is, suppose this link gets shattered, it's not going to wait for 15 seconds and later forwarding. No, the moment it sees that there is a link which is broken, or there is no connectivity on this, there are no hello packets coming within the 2 seconds, immediately this access point will kick in, right? So the access port on this particular switch and this particular switch and also on this particular switch will kick in. They will be in the forwarding mode immediately, and the election process will start. So we are trying to reduce the time frame within which the link comes back, within which the switch understands where to route the packets to which particular switch they have to forward the packet to using the root cost. So that's the only difference between RSTP, that is Rapid Spanning Tree Protocol, and Spanning Tree Protocol. Right? Any queries until now? I know that we have learned a lot today, but VLAN is something which is a little bit big. It is a little bit confusing also, right? So I understand that, but I believe you have taken down notes, maybe taken down screenshots, or maybe also taken down the few things which you did not understand. So you can look it up. If you have any queries, let me know.